Now a matrix is enclosed in either square brackets or parentheses. So for example, the M by N matrix A is denoted like this. This matrix has M rows and N columns. Now, a matrix with N rows and N columns, that is, the same number of rows as columns, is called a square matrix of order N. The entries in row I, column I are said to be on the main diagonal of the matrix. Now the set of all M by N matrices with real entries, that is, real numbers, is denoted this way. And the set of all square matrices of order N with real entries is denoted this way. So no definition. Two matrices, A and B, are equal if and only if they have the same size and all corresponding entries are equal. That is, the matrix A is equal to the matrix B if and only if A and B are both M by N matrices, and for now, with real entries, and the entry in row I, column J of matrix A is the same as the entry in row I, column J of the matrix B for all values of I, which range from 1 to M, and all values of j, which range from 1 to n. So new definition. Let A and B be M by N matrices with real entries. The sum, denoted A plus B, is the M by N matrix obtained by adding entries of the matrix A to the corresponding entries of the matrix B. That is, addition is defined entry-wise. The component, or rather the entry in row I, column J, of the sum A plus B is the sum of the entry in row I, column J, of the matrix A, and the entry in row I, column J, of the matrix B. Now, in the context of matrices, pure numbers, which for now are real numbers, are called scalars. So new definition. Let A be an M by N matrix with real entries, and let C be a real number, that is, a scalar. The scalar product C times A is the M by N matrix obtained by multiplying each entry in the matrix A by the scalar C, that is, the component, or rather the entry, in row I, column J, of the scalar product C times A is the product of the scalar C times the entry in row I, column J, of matrix A. Now, we write the scalar product negative 1 times A as minus A, and we call it the negative of the matrix A. Similarly, we write the sum A plus the negative of B as A minus B, and we call it the difference between A and B. So let's look at an example. So let A be the matrix with columns 4, -3, 2, and 1. And let B be the matrix with columns 1, 2, 5, 7. The sum A plus A is the matrix with columns 4 plus 4, -3 plus -3, 2 plus 2, 1 plus 1. And this is the matrix with columns 8, -6, 4, 2. The scalar product 2 times A is the matrix with columns 2 times 4, 2 times -3, 2 times 2, 2 times 1, which is the matrix with columns 8, -6, 4, 2. So notice that the sum A plus A is the same as the scalar multiple 2 times A, as expected. Now the difference, A minus B, is the matrix with columns 4 minus 1, -3 minus 2, 2 minus 5, 1 minus 7, which is the matrix with columns 3, -5, -3, -6. Okay, so new definition. Let A be an M by P matrix with real entries, and let B be a P by N matrix with real entries. The matrix product A times B is the M by N matrix whose entries are as follows. The entry in row I, column J of the matrix product A times B is the sum from K equals 1 to R, 1 to P, of the product of the entries in row I, column K of the matrix A, and row K, column J of the matrix B. Notice that the inner indices for these factors are the same, and so we call this an inner product. Now we can multiply two matrices, A and B, if and only if they are conformal which means that they have the same inner dimensions further, even when the matrix product is defined, it is not necessarily commutative, and so we make a distinction between multiplying the matrix A on the left by the matrix B, which we call pre-multiplication, and this is denoted B times A. We pre-multiply A by the matrix B, and we distinguish this with multiplying the matrix A on the right by the matrix B, which is called post-multiplication. And is denoted A times B. We post-multiply A by the matrix B. So new definition, a 1 by M matrix is called a row vector, and an n by 1 matrix is called a column vector, so notice that the entry in row I, column J of the matrix product A times B, which once again is the sum from K equals 1 to P of the product of the entries in row I, column K of the matrix A, and row K, column J of the matrix B, is the product of the row vector formed by row I of the matrix A with the column vector formed by column J of the matrix B. The row vector formed from row I of the matrix A is the row vector with entries AI1 through AIP, and the column vector formed by entries in column J of the matrix B is the column vector with entries B1J through BPJ, and this is the sum of products AI1 times B1J plus AI2 times B2J, and so on, through AIP times BPJ.